Okay, we are going to talk about drag force and terminal velocity and friction today. We're going to do a lot of friction. Drag force is a force exerted by a fluid on an object moving through it. So like air is considered a fluid, so when you go through air, that's also called drag force, or any liquid. Air exerts a force upward on an object in free fall. An object will eventually reach a constant velocity, and that is called terminal velocity. Now, in all of our problems that we've talked about, we've assumed we're in a vacuum. Even though we can't live in a vacuum, we're assuming we're in a vacuum. Okay? I thought I gave one to you.
You did.
Fifth period.
Yeah.
Is the gravity okay? If you're near the Earth in a vacuum, is the gravitational force still magnetic?
Yes.
At sea level.
What?
At sea level.
Yes.
There's a question on that on this.
Tension is the force exerted by a string or a rope. It is equal to the weight of all the objects hanging from it. And then also, if we have something moving up, the tension, if we're moving up, is going to be greater. If we're going down, the tension of the string or rope is going to be smaller.
What chapter are we on?
Can you go back one real fast?
Yeah, while she's catching up on the back one. We're on chapter 4. Is that what notes we're going through?
I think so.
Chapter 6 notes this week. We're 2 chapters behind.
They haven't gotten through chapter 5 yet. I think this is just set up beforehand before they know what they're actually on.
But we are on assignment 5.
Yes.
What's that extra hand?
Last week they didn't do assignment.
I don't know if they're... What?
What's that go ahead?
It's 11. 8.5 by 11.
Yeah, that's weird. Why would you put it at 11? That doesn't work fit in notebooks, right?
Well, this is 11, so you're right.
Yeah, don't print mine like, don't cut mine like that, Max.
I don't know. Put it where it looks right. So let's do this problem.
We're on experiment 5 then, or 6?
We're going to do experiment 5. What one do they have on this week?
7.
7. A 50-kilogram bucket is being lifted by a rope. The rope will not break if the tension is 525 newtons or less. The bucket starts from rest. After being lifted 3 meters, is moving at 3 meters per second. If the acceleration is constant, is the rope in danger of breaking? So what we're going to have to do is find the force that it takes to raise the bucket and add that to the weight, because since we're raising it, it's going to be added to the weight of the bucket, and compare that to 525.
Wait, is the tension, force of tension, that's opposite to the weight?
Yes, the tension's up, weight's down.
I printed 3 of them because I had a problem with JC.
So we know M is 50 kilograms. We know D is 3 and VF is 3 also. What's VI?
Velocity initial.
What's value do you have for it? 0. And then in order to find force, we need to know what? Because our equation is F equals what?
MA.
So what value do we need to know that we don't know to find force? Acceleration. So we need to solve for A. What would we use? Knowing this information, what equation would we use?
Yeah, it's only 1 second.
That's kind of random.
We use A equals VF minus VI over T.
We don't know T.
Well, it'll only be 1 second, right? So it's 3 meters up and
It's supposed to be 5 feet
meters
long,
per second.
or 6.
No, what did I say? Half of
Why, what is it?
Well, the last 2 pages were
the
weird.
distance equals.
Or like,
It has like special looking ones. This.
oh yeah, I That's how it was online.
So VF squared equals VI squared plus 2AD. So we have 3.0 squared divided by 2 times 3 is equal to A. So 9 divided by 6. .5. So what force do we have? We're going to have 50 times 1.5 is equal to what? 75. So that's the force from raising the bucket. And then what's the weight of the force? $50 times 9.8. $490. Depends on which type you take. If you're going to engineering, you'll take calc-based. This is algebra-based. So it'll be a little different.
So probably harder.
Harder.
Probably get harder because calc is harder. Right?
So now if we want to know the total force on that, or the total tension on the rope, we're going to have 490 plus 75, and that is 565. So is the rope in danger of breaking? Yes, because the tension is greater than the tension it can withstand, so it could break. Yes. Does that make sense why we add them together like that? Because if you are taking a bucket and raising it, it's putting more tension, right, on the than what? A bucket? A bucket of water, pail, yeah. Okay, so if you raise, or anything, if you raise something up that's attached to a rope, the tension's going to get greater as you raise it up compared to lowering it. So you're going to add the two forces together. Yeah, powdered sugar. Okay, and then friction is a force that opposes motion between two surfaces in contact. It's always parallel to the surface and opposite in direction. So if you're pushing your book across the desk, let me draw a picture of this.
Like this?
Yes, or a crate across ground. If this is your surface and you have your book or a crate or whatever it is, and you have an applied force in this direction, the force of friction is going to be the opposite direction. It's going to be parallel here. Now, next chapter, or the next chapter, I can't remember if it's this chapter, the next chapter, or 2 chapters, we're going to have inclined planes like this, and if you push, have an applied force this direction, our force of friction, again, is going to be parallel to this surface, so we'd have force of friction in that direction. So it's not always horizontal, it's always parallel to the surface. Max, you still have powdered sugar on your face.
Definitely didn't.
It's all
Looks like you've been snorting powdered sugar.
Funny story. One time, in art, you're like, TCFD.
What?
In the back, they have like clay, like glue, like powder, powdered clay. Just add water. You store it, and it gets smaller. It was like something in her nose.
Okay, so let's. Yes, those two are distracting. I'm sorry. So we have static friction, which is the force that opposes the start of motion. If you have something really heavy that you're pushing, you have to apply a lot of force before it actually starts to move, right? You can be applying a force to it and not have it move. So that's called the static force, or static friction, which is equal to the force that opposes the start of motion. Once the object is moving, then we have sliding or kinetic friction, which is friction between surfaces that are moving. And that sliding friction, once you get something to start moving, a lot of times you don't have to put as much force into it anymore, and you can keep it sliding at a constant speed. So to do friction, you have to have normal force, F sub n, and normal force is always perpendicular to the surface the mass is resting on. And it's numerically equal to the weight as long as we're on a horizontal surface. So if I have this surface again, and I have this object, and I have a weight force coming down, my normal force would be going straight up. And since they're opposite in direction, then they're equal in magnitude. Now when we get to inclined planes again, whoops, that's never a good inclined plane. Let me do a better job. Like this, and I have an object resting on the inclined plane. Weight is always just straight down. That's not very good either. I wish they had the undo button over here. I wonder if I can change that in my settings. There we go. So weight is down again, but normal force is perpendicular to the surface, so it's going to look like this, and when we get to this point, normal force does not equal weight. So only if it's on a horizontal surface does normal force equal the weight of the object. Force of friction we symbolize with F sub F, and F sub F is equal to mu times the normal force, and mu is the coefficient of friction. And a coefficient of friction depends on the two surfaces that are in contact. So if we have two rough surfaces in contact with each other, the coefficient will be a lot higher. If we have two smooth surfaces in contact, the coefficient will be smaller. There's also a coefficient of kinetic friction and coefficient of static friction. So whether or not an object is moving or not is going to change the coefficient of friction. But for those two materials that are in contact, that coefficient of friction is constant. So if the same two surfaces are in contact and they're sliding, they're in motion, that coefficient will always be the same for that. For those two materials. Questions on friction? If we go to do some problems now, maybe? When we look and see whether or not an object with friction is going to be accelerating or not, because we can be moving an object, have friction, and be moving at a constant rate. We need to, in order for something to be accelerating, we have to have a net force of greater than 0. So if we look at net force, it's going to equal the force applied minus the force of friction, because they're in opposite directions. You have to subtract them. The net force is equal to the force up minus the force down, because they're in opposite directions. And tension minus the weight. Now, yeah, that's going to depend on whether you're moving up or down, I guess, really. Right here, out in front, right here. Sigma, it means net, the sum of all the forces. So the net force has to be positive in order for an object to be accelerated. Let's try a problem. A smooth wooden block is placed on a smooth wooden tabletop. You find that you must exert a force of 14 newtons to keep the 40 Newton block moving at a constant velocity. Since we're going at a constant velocity, what is our acceleration? Constant velocity. What's our acceleration? 0. It's not changing speeds. It's not accelerating. It's not decelerating. Okay. What is the coefficient of friction for the block and table? So let's draw a little picture up here. From now on, a lot of times on your tests or quizzes, if you have, like where you have to give givens and unknowns, you can draw a diagram as long as it's a free body diagram labeled and everything. That'll work. What? Can I draw one and then you label it? No, you have to draw it. Because. So here is our weight. Weight is down, right? What is the weight of our block? $40 newtons. So what's our normal force? We're on a horizontal tabletop. So our normal force is equal in magnitude as our weight. So it is also 40 newtons. Now, since our acceleration is 0, do we have a net force? No, our net force is also equal to 0. That means that our applied force and our frictional force have to be equal to each other. They're equal and opposite, since there is no net force. So force applied is equal to, what's our applied force? 14, yep. So that means our force of friction is equal to 14. So if we want to find the coefficient of friction, what's our equation for friction? Mu times normal force. So if we're looking for mu, our coefficient of friction, we're going to take the force of friction, which is 14 newtons, and divide by our normal force, which is 40 newtons. And get our coefficient. What is it? 0.35? 0.35? Okay. Now, since we took a Newton divided by a Newton, does our coefficient have a unit? Nope, it's unitless. No units. So our answer for that would be 0.35. Now, this coefficient will always be the same as long as that block, that same block and that same table are in contact and they're moving. So for the next question, it says if a 20 Newton brick is placed on the block, what force will be required to keep the block and brick moving at a constant velocity? So again, if we're going at a constant velocity, our acceleration is 0. So our force of friction is equal to our applied force. So if we can find the force of friction, that's equal to the force we have to apply to keep it going at a constant velocity. And, well, our normal force will change because we have more weight now. If we have a 20 Newton brick on here, what's our weight going to be now? Yep, let me change color here so I can... Ooh, you can't even see that, can you? So that means that our normal force is also 60 newtons. But we can still use the same coefficient. So now our force of friction is equal to 0.35 times our normal force is 60. Now, if it said that the brick was under the block and the block sat on top of the brick, we couldn't use that same coefficient. But since that block and the table are still in contact, we can use it. So what is the answer? 21? Okay, so that's 21 newtons. And that is the amount of friction. So if we want to move it at a constant velocity, we're going to want to apply 21 newtons of force also. Do we have any questions on that? Okay. Let's try another one. I think we have lots of problems that we can try. It doesn't. It has to do with net force. Suppose Joe, who weighs 625 newtons, stands on a bathroom scale calibrated in newtons. What force would the scale exert on Joe? If he's applying 625 newtons downward, what force would it... The scale is pushing 625 newtons upwards. He's not moving. If you're just standing still, you have to have a net force of 0, so there has to be an upward 625 newtons. So in what direction? It would be upward because weight is down. If Joe now holds a 50 Newton cat in his arms, what force would the exert on him? 675. If Joe puts down the cat and his father comes up behind him and lifts upward on his elbows at a 72 Newton force, what force does the scale now exert on Joe? 553. You just subtract 72. Okay. Does that make sense, those questions? The direction, so if he's... Yep. If he's standing right here and the weight is down, right? He's not moving downwards, so that means that the scale has to exert an upward force. Okay, the coefficient of friction between rubber tires and wet pavement is 0.5. The brakes are applied to a 750 kilogram car traveling 30 meters per second, and the car skids to a stop. What is the size and direction of the force of friction that the road exerts on the car? So basically, yeah, we're looking at force of friction. Are we moving at a constant velocity? Let's draw a picture here. Are we moving at a constant velocity? No, because, so, I guess it's not asking for the applied force. It's just asking for the force of friction, huh? So our force of friction is equal to mu times the normal force. And our normal force is equal to the weight, because we're on a horizontal road. So what's the weight of our car? 7,350. And we know the coefficient mu is 0.5, so our force of friction then is equal to 0.5 times 700, 350. So what's our force of friction? Half of that. 3675. 3675. Very good. Questions on that one? Okay. What would be, okay, this is still applying to that question, okay. What would be the size and direction of the acceleration of the car? That's what we're looking for here. So now, what do we know? We know VF and VI, don't we? What's our final velocity? And our initial? 30. And then what else do we know? Okay, let's draw a picture too. Yes, Zach? No. Because we have too much, we're already behind. We're having egg rolls for Mold Day, so that's...
Egg roll.
So we have weight, we have normal force. Let's draw all of our forces in here. We have the force of friction.
Did you ever change it so you could hear our questions?
I don't know how.
I can barely hear you as you're watching.
Really?
Yeah, and I can kind of hear like it answers the questions as it goes. Not my dumb questions, but like actual questions.
I didn't.
We should change that so it picks up. Because remember how you said you turned it way down?
No, I turned it up. I turned the input up.
Oh, questions.
What does size and direction mean?
Magnitude and direction.
Like what would...
Like magnitude would be like the 30 newtons or something. And then direction would be like to the left or right or... Okay. So let's say the car is moving in this direction. What direction is the acceleration in? Same direction or opposite? It's decelerating. So the acceleration has to be opposite. Okay. Size. We don't know the applied force. Right. I'm trying to figure out how you. I don't know if we have enough information.
Faulty problem.
What are you thinking?
I don't know.
Just say it took 10 seconds for it to stop.
Because they don't give us a time or a distance, huh? And we don't have an applied force, because we could find, if we had an applied force, we could find a net force, and that's equal to ma.
What's that little box thing?
This?
Yes.
Sigma? Oh, that's our car. I just draw everything as boxes. It's easier that way. I'm thinking we don't have... enough information. If we had an applied force, we can find the net force and find acceleration that way. I say you just cross that out. So now we only have two more. A rubber ball weighs 49 newtons. What's the mass of the ball? How would you find that? Oops. 49 divided by 9.8. Because we'd have weight is equal to mg. What do you get? 5? 5 kilograms. What's the acceleration of the ball if an upward force of 69 newtons is applied? Right, if we have a ball, we have a 49 newton force. Oops, that's supposed to be 49. 49 newton force upward, or downward, because that's the weight. And we're applying a force upward of 69 newtons. What's our net force? 20, right? So we have a net force of 20. So now if we want to find the acceleration, we'd have to use that as equal to ma. So you divide by n, so we have, oops, man, this board is giving me fits. 20 divided by 5. So we'd have 4 meters per second squared. Do you agree? Okay. And last one. Spring scale hangs from the ceiling of an elevator. It supports a package that weighs 25 newtons. What upward force does the scale exert when the elevator is not moving? So if it's not moving, what force would it have to exert? 25 newtons, right, because it's not accelerating anywhere. So the net force has to be 0, so they have to be equal.
We have all the classes, they're just short.
What upward force does the scale, what force must the scale exert when the elevator, an object, accelerate upward at 1.5 meters per second? Is this our first early dismissal then of the year? To find our net force, you're going to have to find the mass of that package, right? And multiply it by 1.5. And then add those two forces together. So you're going to take 25 newtons divided by 9.5, or 9.8.
Grade
What is
sheets
that?
will be distributed after school in the following rooms. Grade 7, Mr. Foster, room 106. Grade 8, Mrs. White, room 110. Grade 9, Mrs. Greenholmes, room 209. Grade 10, Mr. Carlin, room 107. Grade 11, Mrs. Shuck, cafeteria. Grade 12, Mrs. Wright, room 210. There will be a short meeting for those girls interested in going out for junior high basketball on Wednesday after school in the auditorium.
What do you get here?
J.E. Beeman, Paige Fernholtz, Nicole Glover, and Tara Phelps report to the band room after school. Call for tonight's choir concert, 6:30 Madrigal, 6:45 9:10 Select.
What is it?
7 o'clock Varsity Choir, 7:10 9:10 Choir. Michael Lindblad, Haley Hall, Zach Hollister, and Paige Fahrenholtz see Mrs. Johnson after school. Stop in at the book fair in the library. It is open before school, after school, and during lunch all week. There will be a very short meeting for all boys tennis players in Coach Hartman's room today after school. Football players are reminded to get your jerseys back from whoever borrowed it last Friday. Mrs. Johnson, call the office.
Okay, just add these two and we just have 28.83 newtons. There you go.